Good morning, everyone. My talk is Earth's gravitational coefficient (GM) and geosynth motion determination using LEO GPS data. First, let me a little bit explain the. So I think this morning already a few presentations talk about geosynth motion determination. What's the difference is here I just use one LEO satellite. Before, I think most days use, the main difference is they use multi-satellite data. Okay. Second explain is what here shows both GM and geosynth. Actually, geosynth motion determination we have already studied 20 years ago, and the results are already published. But for the gravitational coefficient GM is the first time. Yeah. Okay. Before I show you the results, let me give you the background and the motivations for this study. As you know, GM and geosynth motion are very important for realizing ITRF. The GM has effective frame scale, and geosynth motions directly affect the frame origin. So the current conversion GM value was determined 30 years ago using SR data. Currently, either GM or geosynth is determined from SR. And if you look at recent paper or results, the GM solution from SR is not so stable, changed with the time, year by year. So of course, we can also use LEO, determine both GM and geosynth. So the questions are, how well can we determine GM and geosynth by using just the LEO GPS data? Second question is, what is the main impact on GM and geosynth parameters? So based on the motivation, we set up our study goal. First, we investigated the method of LEO GPS-based GM and geosynth motion determination. Then we studied main effects, such as POD radius bias, reference frame antenna offset, and so on the GM and the geosynth motion determination. Finally, we will access our solution through internal and external comparison. So before I show you the results, let me briefly describe our method, which is used for determining the GM and geosynth motion. For GM, also some called degree 0, we use a so-called dynamic method. This means we treat the satellite as a moving object whose motion can be described by dynamic model. One of them is a gravity field model, which includes GM parameter. When we do the POD, usually the GMs treated as a given parameter, is a known parameter. But when we treat the GM as an unknown parameter, then we can determine the GM. For geosynth motion, we use so-called kinematic method. So when you describe the geosynth motion, you need a reference point. Here we use a so-called center of network by through the fixed ground station coordinate. The satellite is around cm. So our method is to directly to determine the 3 geocenter offset coordinate between cn and cm. This table shows you the used data and estimated parameters. For this study, we use so-called double difference carry phases. This means we need 2 receivers. One we use ground, one is LEO. For GNS satellite, we fix the orbit, clock, colonial, the product from IGS. For the estimated parameter, we separate mainly the 2 different kinds of parameters. One is local, one is global. For the GM and the geocenter, we solved just monthly. Other parameters treated as local is daily. We process it daily. For daily parameter, we have one only important the parameter so-called onboard antenna correction. Later, I will explain why it is important. This is try to understand the relationship between GM and orbit. So based on the Kepler third law, you have equation 1. From equation 1, you can derive the relation between GM offset and the offset in radial direction. If we assume the satellite is circular, then the offset from GM causes the constant in radial direction bias. Based on equation 2, we can derive the equation 3. This is effect on orbit scale. So you can say from the equation 3, it should be no, it doesn't matter the satellite height. For equation 2 and equation 3, I will prove the use 3 different POD. So this slide shows you the test data and the test cases. For GM and geocenter, we use more than about 20 years of data from GRACE and GRACE follow-on. The POD, we just use 1 year to prove the equation 2 and equation 3. Here, I just show you 7 different test cases. Next, I will show you each case. So this slide shows you the effect from GM on satellite orbit and scale. So I assume the GM offset is, this is so-called uncertainty from current GM. So top right figure show you the effect on orbit. Here is I compared between with and without the offset. So you can see the effect mainly is on radial direction. Top right table show you the 3 different satellites. The middle rows show you the values computed based on what I showed you, the equation 2. Bottom is show you the based on the POD difference. So you can see almost the same. So this means the equation 2 is proved used here. Bottom table show you how effective the orbit scale. So you can see the effect on offset, rotation, almost very small. You can ignore. But for the scales, is relatively big. But the value is almost same. And also very close to what I, based on the equation 3 computed. So this means you can see the effect on scales Doesn't matter the satellite height. Okay, I have to quit. So this figure shows you the time series for more than 20 years, and we just use 1 month state. This is monthly solution. So the correction is very, I just show you the correction. You can see the mean standard deviation, the RMS, same level, 10 minus 6. The variation is very small. If you look at it, compare with SR, is 1 magnitude smaller than SR. This means we can just use 1 month, we can get a very stable solution for GM for 20 years. Okay. So based on the equation 2, you know the GM very depend on how good your orbit, particularly in radial direction. If you have a radial direction bias, then your GM is biased. So therefore, here I show you the effect from antenna offset. Here the comparisons between with without the antenna offset correction. The magnitude is about 1 millimeter. So you can see when I estimate antenna offset, the solution is very stable. When I don't solve it, I assume the antenna offset is correct or absolute, then has compared to estimation is a little bit variated. But the magnitude is still small, about 10 minus 4. So this means if you have about 1 millimeter error or something, then you cost 10 minus 4. Current actually is about this level. So here, maybe do time. Okay, so here I just show you the time series about 20 years. The geosynth in 3 different directions, X, Y, Z. You can see before 21, the solution is stable, but after 21, the Z direction is a little bit higher. What is the reasons I just guess is because I use the system's IGS 20. IGS 20 use data is till 21. So because my method is limited or very dependent on how good is the station coordinate. This table, I just comparison our solution with the recent XYZ. So you can see X direction is there are 2 groups. One is about 1 millimeter, second is about 2. So our solution is, I just want to show, we have Grace A, Grace B, we can separate for internal comparison, and same time I also use a different time period. Because such as for these different time period, they have a little bit different. So from X, our solution very close to so-called the ITF 2020 geosynth motion model. For Y directions, most solutions very close. Big the difference in Z direction. So this is, before you already know, the Z direction not so, yeah, sorry. Yeah, so let me summarize my talk, okay. So based on this start, we know the GM is a GM geosynth, we can use layer data determined. And main effect is antenna offset. This is, you know, antenna offset is not only for me, for everybody, such as if you have no absolute antenna in direction GS satellite, you cannot get a good scale. So this is the same problem. So therefore, I just suggest for future satellite missions such as Genesis, it is better is on the ground, very carefully calibrate, try to get the absolute value. Then When in the flight, we don't need in-flight calibration estimated. So, yeah, that's all my talk. Thanks. Okay.